This is a continuation of my video series on cluster analysis. If you're not already familiar with cluster analysis, this video will be much easier to understand after watching part 1. Last time we went over different spaces and connected components. Connected components is actually a very good stepping stone into this video because a lot of the algorithms I'm about to talk about are heavily rooted in connected components. We're also going to look at how connected components is limited and why we need these more complex algorithms. As a reminder, the principle of density-based clustering is that clusters are defined by the density of the points within them. As a result, contiguous shapes like this smiley face can have their components easily identified. So looking back at connected components, you can see it's actually a density-based method. It has a pretty loose definition of dense though, like this point out here. Close enough. That's not going to cut it anymore though. We're going to make a touch of an improvement that I like to call close components. Close components says no. We may be connected, but we're 40 units apart. I only accept being 10 units away at most. But this is density based, so let's say there were 3 points in between. Suddenly, we're connected. So now we're going to update our interfaces to allow for that. First, we're going to have to modify our IMetricSpace interface to use floats for distance instead of bools for connectivity. We'll replace the bool in distance with a float and add a float distance argument to add connection. Now all of our space implementations are outdated. So in Node, first we're going to replace our hash set with a dictionary of nodes to floats. So given another node, we can look up its distance. Then we'll add the distance argument to add connection and pass that along as the value to the dictionary. Finally, we'll rename isConnected to distance and return the value associated to the node from the dictionary. We can't just assume it's there though. So first we're going to check if the key exists and return not a number if it does not. Not a number will be our sentinel value to indicate there is no connection between points. In the graph shape, we can now take the distance as an argument for add connection and pass it along to node.addConnection. Distance now returns a float, and we're done. The matrix shape is now a 2D array of floats instead of bools, and we set the value of the floats to the distance. We also need to initialize every cell as not a number. The sparse matrix shape is now a dictionary of matrix cell pairs to distance, so we need to add distance to add connection, and again check contains key before returning either the dictionary value or not a number. Now, to fix connected components, we just check that our distance is not a number, and we're solid. But we're about to change it a little more. First, we're going to add an argument range. Range defines the maximum distance that a point is considered close. By default, we're going to make this positive infinity, because when the range is infinite, we just have connected components. We're also going to add range as part of our context, so we don't have to pass it into create cluster. Then we're going to replace checking not is not a number with distance is less than or equal to range. This still works as connected components too, because not a number will always return false when compared with any float, even positive infinity. Now this is better, but close components still isn't often a great solution, as I will demonstrate. So back to this view, but now we're going to add a whole bunch of other points. Now there's a problem. These clumps on the left and right should probably be different clusters. But because we define dense as having any single point between them in range, they're connected. One algorithm that solved this is density-based spatial clustering of applications with noise, better known as DBSCAN. DBSCAN introduces the concept of a core point. A core point is considered to be strongly connected to the cluster, so all its seeds are added to the cluster if not already a member of another. DBSCAN defines seeds as being all points within a defined range, epsilon, and a point is considered a core point if it has a certain number of seeds, min points. Here, our range is defined by this circle's radius, and our min points is 3. So here you can see that this point is a core point because there are 3 points within its radius. However, these points aren't core points because there's only 1 or 2 points in their radii. These white points are noise. They aren't in the radius of a core point, so no cluster can claim them. One more thing to look at is this core point. One of its seeds belongs to another cluster. This is because the other cluster got assessed first and had already claimed that point. This is fine. The algorithm allows for that. For the DBSCAN code, we'll start by just copying connected components because it's very similar. Then we'll add a min points argument and again pass that to our context. Now we're going to rename create cluster to try cluster, make the cluster an out parameter, and make it return a bool instead. Before we make any clusters though, we need to add a method for getting a point's seeds. GetSeeds will take a point's index and return the indices of all seeds to that point. Back to try create cluster, we'll start with that list of seeds, and if there are fewer seeds than min points, we'll assign the point as noise and return false. If there are enough seeds though, we can create a new cluster containing just that point and expand it with expand cluster. Expand cluster will use our list of seeds as a stack and run a depth first search on our graph, adding each point to our cluster. If any of those points are core points, their children will be added to the stack. Finally, make cluster only add the cluster if try create cluster returns true, and call expand cluster from create cluster. Now we're going to take a look at our next algorithm, ordering points to identify the clustering structure, better known as optics. Optics was designed to solve DBSCAN's issues handling clusters of variable densities. It does this by linearly ordering points based on their reachability. Let's look at what that means. Here, this red circle is epsilon. Epsilon is the max distance for a point to be considered another point's neighbor. It is only there for optimization to reduce the number of points queried per iteration. Ideally, the result should behave as if it were infinity. This green circle is core distance. The core distance spans until it contains min points. In this case, min points is 3, so it spans until the core distance contains 3 points. Optics then tracks the reachability of each point. The reachability for seeds is the core distance, and the reachability for all other neighbors is just their distance. Finally, the reachability of the initial point is infinity. Now we progress to the point with the lowest reachability and repeat, except we'll only update the reachability if the new reachability is lower. We also won't update the reachability on already processed points, so our infinity stays infinity. So if we run through this on this section, through to completion, our reachabilities would be this. So now we once again go to the next lowest reachability, which is here. There aren't many points nearby, at least relative to their other neighbors, so there's not many updates to make. Continuing again to the lowest reachability brings us here. There's a lot of repetition, so let's just watch the animation fast forward through the rest of the algorithm. Finally, now that we have the reachability of every point, we can plot them in the order that we process them. There's many ways to assess the clusters from here, but the principle is that once the reachability drops below a certain threshold, you begin a new cluster, including the value before. You also may find that once it goes above a certain threshold, you're probably looking at noise. One thing that's really powerful about this algorithm is that once you've run the clustering, you can reassess the cluster threshold without rerunning the intensive part of the algorithm. Now for the code. Except, okay, the code is there. I wrote the code. It's on GitHub if you want to see it, but I hate screen recording it and that whole process. Plus, I just don't think it's a very useful section. So, here it is. Go see it on GitHub. But, yeah. So that was a deeper look into density-based clustering algorithms. Thanks for watching. Next up will be a video on centroid-based clustering algorithms. And yeah, so small channel update as well. I just graduated from university and I'm yet to find a job, so maybe they'll get me out of this biennial upload schedule, but who knows? Time will tell, I suppose.